Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry video for you all. And of course, our new topic is all about equations of circles. Now, this is still a part of our conic sections unit, but now we're going to be moving further into the equational and algebraic forms of these units. Not just formulas, but more graphical terms, something that you're going to refer to more in algebra in general, and specifically algebra 2. So we're going to be looking at equations of circles in two different forms, which is standard and graphing form. Obviously, there are two different purposes that you're going to be given these forms, and also I'll also be going over that in my next video, more graphing form in my next video on parabolas. But today we're going to be mainly focusing on the standard form for circles, really identifying what circles are, and also correlating parabolas as well, introducing them, because we'll be focusing on parabolas not very thoroughly. We're just going to be focusing on the different equations for parabolas and two very important principles and parts of parabolas, which you don't often cover, in algebra 2, because it refers more to distance principles and in terms which actually refer to geometry. So it's going to be directrix and focuses of parabolas, which I'll be getting into it later. So a bunch of exciting stuff coming up. But for now, let's look at the fundamentals of our equations and then build up off of that. So today's purpose for this lesson is to take a look at the equations of circles and some of their special properties. Now, we know equations also represent special properties of circles. So we're going to be taking a bit of our fundamentals, what we know about circles already, and correlating them with these graphical equations. So without further ado, let's jump right into it. And also, before we get into that first slide, please make sure to subscribe down below. Don't forget, hit that like button on this video and turn on post notifications so you're updated on every single one of our newest posts. Also, feel free to utilize the comment section down below as well. We really pay attention to what you put out there and all of your constructive feedback. So let's get right into it. So equations of a circle, part 1. Let's look at the real-life application of circles. So we know that circles, are existent shapes, but let's look at why they're actually important and how equations are actually very important in representing them in real-life scales and in real-life situations. So circles are harmonic shapes that show fluid motion in real life. That's basically the overall consensus. But now if we look at that in a graphical sense, we know that circles, when graphed, can be adjusted as dilations under a constant equation, and their expansions and contractions. So the reason that I put that in the order in which it appeared is because harmonic shapes are something that you can actually refer to in real life, something that's always constant. But then again, what we're always prioritizing first is going to be our geometric terms, our geometry, how we correlate it to geometry, and then of course afterwards we're going to correlate it to real life applications. So I like to show you how contractions through dilations are actually also very important. That's what this equation is all doing. So you're given a base equation, maybe your standard circle that has a center at your origin, 0, 0. That's your central circle. I don't want you to get too confused with what I'm saying. I just want you to focus on what that circle might look like. Think of a circle with the central point. That central point is going to be on the origin, and it's going to have an equal radius going about just as any other circle would. Now, think of that circle as your basic circle. Now, this equation is basically just going to take that basic circle, utilize the relationships that are given, and it's going to give you different variables in which you can adjust to dilate or contract that circle. That circle is going to stay the exact same, unlike triangles or rectangles, excluding squares. Just like squares, you're going to have the same dimensions and same relativity within the circle, which makes it much easier to develop a simpler equation in which you can do a lot more with a lot less information given. And this is a real-life application right here. So this is a Ferris wheel. This is a very important circle. And the reason that I wanted to put this out is because it's a harmonic shape. So I want to put this down here for just basic qualities of circles. So I'll say qualities of circles. And these are all real life. I'll say real life here, not just geometric properties. Of course, geometry correlates to real life, but these are more simplistic terms that have a much more general meaning. So we have qualities of circles. 1, they're harmonic shapes. So if you think about music, you think about harmonies. Harmonies are basically notes, or basically various valves of notes that are strung together in order to create a one entire piece or one entire given culmination of notes that actually has a harmony. And harmony in terms actually means an organized output. So harmonic shapes like a circle are basically what have strung together different points on a given grid. And in this case, it's going to be different given lines that are actually going to be strung together. And in that manner, they're going to be strung together in a given harmony, in which to actually produce a circle that has no identified length. However, it does have an equal curvature all the way around, and it's going to be the same exact consistency, meaning radius and diameter are always going to be the same. And then another quality of circles, they're always going to have same relations, so interior relations. This basically means that all of the interior properties, such as radius, diameter, chords, and arcs that are all developed, tangents, secants, they're all going to have some sort of relationship and ratio amongst each other. That's why we can actually develop so many formulas within circles that we can't develop within these other polygons that actually have straight edges. And finally, they are all similar to each other. And this kind of really goes with this point here, because their interior relationships and basically their proportions are all alike amongst all circles. That means you're just going to have the same exact similarity between any type of circle that's existent. And if they're not similar, if two items that are not similar, that means one of them is not a circle. Perhaps both of them might not be circles. That's an easy identifier right there. This is due to the fact that the degree in which a circle actually turns in order to actually envelop itself and turn at an equivalent amount of degrees, it's going to be at a specific degree measure over given sectors and given proportions. So that's always going to be consistent. Now, I know I spent a lot of time on this, but it's very important to recap and look at circles in a different perspective. But now, let's get into equations of a circle part 2, and let's actually look at our newer equations. And today, in this slide, we're going to be focusing on the standard form equation, basically our focus for this lesson. So basically, when we look at standard form of a circle, it's going to be your simplistic equation for a given circle. It's much easier to deal with. As you can tell, graphing form, which is our other form for a circle, is most likely going to be utilized, in calculating and actually graphing that given circle and actually interpreting what a given circle is and converting it into equation. It's much easier. But standard form is the opposite. It's much easier to interpret into a graph and also to interpret its separate parts. So the standard form of a circle is a circle with center h, k, and radius r. Has this equation, which is x minus h squared plus y minus k squared equals r squared. So in essence, what's really going to happen here is you're only going to know your h and your k values. Your h and your k values are your manipulating values as well as your radius. But your radius might be something that you're trying to discover or recreate. And one way in which you can do that is if you're given a central point and, say, for example, another point on the circle, you can easily calculate this. You would take your h and your k values, you'd plug them into this equation. You make h your negative h value. Say, for example, h is 3. Let's say that our value is 3, 4 is our center. We plug in 3 for h and we get negative 3. And then we plug in 4 for k and we get negative 4 here, just in terms of this equation. And then what we would do is we take that other point that was existent on that given circle and we plug it in its x values in. And say, for example, we'll just leave it as x and y. So we subtract these values, multiply them out, and I'll show you how to do binomial multiplication and multiplying perfect squares. And then in order to do that, in order to discover a radius, we'd merely multiply those add them together. They should be like terms because they're all being given integer and digit values. And once you square them and add them together after you FOIL them, then you'll finally get your radius squared, square both sides, and you'll merely get your radius of your given circle without even having to graph anything. So the center of the circle as well as the radius must be known in order to develop the equation, one or the other. So all I'm saying is, if you're given a radius, then all you need to know in this term would be one other point that's given on the circle in order to find the actual center. Otherwise, you would need to be given the center and, like I said, another point on the circle. So one variable that's always going to be consistent in these problems that we're going to be working on is basically a point that's already existent on the outside of a circle. So say, for example, we have this graph here. And we want to figure out what the radius is. I know we can just utilize this x-axis here, but let's imagine that x-axis is actually not numbered. So let's imagine that it has no numbers, but we're only given our origin. And then again, graphs don't always have to increase in steady amounts. So that's our origin right there. And we'll say that origin, so let's say origin equals center of our circle. And then let's say that another point on this given circle will be 0, 4. Or sorry, 4, 0. 4, 0 is going to be that common point. And we're trying to figure out what the radius is. What is our r value? So let's plug these values into our equation. So we get that x minus h squared is going to equal times plus y minus k squared equals r squared. We're going to plug in those values that we know. So we know that it's a center, so our center or origin is going to be 0, 0. So we have our x value is 4, so it's going to be 4 minus 0 squared plus we have a 0 minus 0 squared because that's our y value. And that equals r squared. Now we're going to multiply this out, and we get 4 squared equals 16 plus 0 equals r squared. 16 equals r squared. And we're going to square root both sides, but we know that 16 is already a perfect square, so we know that it's going to be 4. So r equals 4, radius equals 4. And then from there, we can determine things like the diameter equals 8. We can determine chord ratios, tangent ratios, things like that, and secants. And so it's very essential and very important. Equations of a circle part 3. Let's look at general form or graphing form. So the general form of a circle, if you know what standard form is for a given parabola, this kind of looks quite similar with the ax plus by plus c. But now since it's a circle, we're actually adding on those two squared variables, our x and y. Those values are always going to be squared. So we have our x squared plus y squared plus ax plus by plus c equals 0. So these equations would later simplify into two multiplying binomials. So if you take a look at the equation that I had previously shown you with standard form, general form is basically just that equation factored out. Just think about it. When you're taking two values and you're adding them together and squaring it, it's not merely just adding those two values and there's going to be separate squares, like a plus b squared. It's not just always going to be, it's not going to be a squared plus b squared. It's going to be a squared plus b squared plus 2ab. And that's what these extra variables are representative of. And when you actually FOIL them back, when you FOIL out your standard form equation, you're going to get this equation, this stretched out equation, which is actually much easier to utilize when trying to rewrite the equation of a circle when looking at its graph. So it's very important that you know both of these because both of them are going to be very useful. So let's utilize the same exact points that I had shown you before. Let's say that our center equals 0, 0. So with the center at 0, 0, that's something we can identify from the circle. Now, apart from a standard form equation, what we're going to do here is we're going to try and identify how to actually bring out that given equation in our circle, from our circle, and actually, solve for A, B, and C. So that comes with the quadratic equation, which I'll show you on the last slide. But we'll get into this later on. I'll do a separate video on general form because it's actually very important. I just wanted to introduce standard form and general form in general, but I will go over that later. But let's just look at how we break this equation down. So if we're given like one point on this circle, such as 0, 0, all we would do is plug in our values for our x and y values. So we keep the x and y the same, and we try and solve for A, B, and C, what these values are. These values are basically your constant multiples that you're multiplying out to your x and y values in order to achieve your given circle. Just like in a standard form equation, it's going to be ax plus by equals c. So just like that. So here we're going to plug in 0, 0. So we have 0 squared plus 0 squared plus 0 plus 0 plus c equals 0. So now we can automatically solve for c. We know that c equals 0 automatically. So once we plug in those values, we can start to solve for a and b, and in which you would multiply out 0 to each value. And you can tell that b would also, b and a values could be integers, or it could be integers, or it could be a 0 or negative, just 0 or integers. And when you know that c equals 0, we have a very strong knowledge that ax and by are most likely, they automatically equal 0. So that means the values of A and B are not going to matter anymore. So A and B are unimportant after this point. If C automatically equals 0. Because C is going to be your constant, and when X and Y are going to affect your A and B, and when everything else equals 0, I mean C is automatically going to equal 0. And because you already know that C equals 0, you can utilize a quadratic equation. Therefore, you wouldn't need to separately solve for A and B. You can just use the quadratic equation, and A and B variables as their own are not going to be important in this equation. So equations of a circle, part 4. Let's look at binomials. So the binomials A plus B and A minus B are conjugate binomials. Basically, that means that they're opposite binomials. They're going to contradict each other. So that should be a T here. I apologize. So their product is equivalent to A squared minus B squared, which is the difference of squares. And the addition of squares would be A plus B times A plus B. So that's what we're going to change here. The addition of squares would be A plus B times A plus B instead of that minus B. And that would give you a different answer. So what basically happens here is I'm going to show you how to actually FOIL these values out. FOILing is a process in which you multiply two different binomials together to get a trinomial. So for F stands for first. O stands for outer. I stands for inner, and L stands for last. So that's basically what you're going to do. You're going to multiply these values, A times A, B times negative B. That's what you're basically going to do, and then you're going to multiply likewise and calculate those values. Now, I'm not going to get too much into depth with this. You're going to learn this in Algebra 2 if you haven't already went over this in Algebra 1, but I'm just going to show you how to actually do it. So we have A plus B times A plus B. We're trying to multiply these out and simplify them into a trinomial, which is basically 3 values. A plus B times A plus B. So we get A times A, which is A squared. And then we get B times B, which is B squared. And then we're going to multiply our A's and B's together. So we get B times A is going to be AB. And then A times B is going to be AB. So that's going to be 2AB. That's what we get for the addition of squares. A squared plus B squared plus 2AB. And this is just going to be A squared minus B squared because those separate values actually cancel themselves out. Circles and parabolas, part 1. Let's look at parabolics. Now, I know this is about circles, but the actual equations for circles and parabolas are actually derived from similar roots, and they actually look quite similar because they are very similar in their identification and their graphing. So a quadratic equation written in standard form, ax squared plus bx plus c equals 0, where a does not equal 0, you can use a quadratic equation. Like I was saying before, in our general form, you can actually utilize a quadratic equation similarly and correlate it to a given actual parabola. So in this quadratic equation, we're gonna utilize this this standard form in which ax squared plus bx plus c equals 0. Because remember, we're going to be utilizing circles and parabolas together. And what we're going to do is we're going to utilize this quadratic equation and basically figure out different variables. And in this case, the quadratic equation is actually in terms of x. So once we calculate what our x value is, we can merely calculate what the whole equation is. And that's when we're given our variables a, b, and c. Likewise in our general form equation. So I'm just going to utilize this equation here. So the equation is that x equals negative b plus or minus, and I'll get into what that means, the square root of b squared minus 4ac. These are all in terms of these 3 variables as shown. B squared minus 4ac over over 2a. Apologize. Over 2a. And all this is basically saying is you're going to take your values and you're going to plug them in. I don't want to get too much into depth, but I'm just going to explain this. So you're going to plug in your values for, b. Once you're given these 3 variables, you only need 2 of those given variables to solve for a given number. However, you would, in your general form equation, However, in this equation, you need all three variables given in order to calculate what your actual x values are, and then therefore you can develop what your y values are, because y is actually going to be equivalent to 0 as shown. So you could plug in your negative b value, and you can basically calculate what's within the parentheses first. So you do b squared minus 4ac, and once you calculate what that value is, the reason why it says plus or minus the square root of that value is because whenever you're square rooting a given value, say for example you're square rooting 9, it has two sets of square roots. It has 3 and negative 3, because negatives multiplied by each other are going to equal a positive number, like 9. So in this case, it could be either or value, and you have to see which, and both values will actually be applicable to the situation. So there's always going to be two solutions to that, and those are going to be where your actual parabola crosses the x-axis, just as your circle will also cross the x-axis. And finally, we have completing the square. Now, this is also another complex topic, which you will get into more in Algebra 2. This is basically a fundamentals. I haven't gotten into really problems yet because I just want to get you guys familiar with this. So this is called completing the square. You can complete the square by taking a binomial and adding b over 2 squared to get a perfect square binomial. Now, all that's saying is if you're given an equation in a trinomial, like the actual standard form equation like I was talking about, how you're given those two binomials multiplied by each other, that's going to equal a trinomial. So let's look at the other way around. We learned how to FOIL, which is basically taking two binomials, making them trinomials. Let's look at the opposite way, taking a trinomial, putting it back into a binomial. I just want to put this out there. If you don't have a smooth way to make a perfect square, this is a smooth way to make a perfect square binomial, and I'll show you how to do that after this, after I show you the basic completion. So we have here, let's make this example here. So we have x plus 12x plus 36. Sorry, x squared plus 12x plus 36. This is our standard equation. And in this equation, what we want to do is make this into two binomials that are going to be multiplied. Preferably, we want them to be squared. However, just two binomials multiplied by each other, as shown in the standard form equation of a circle. So first step that we would do is try and factor out any values that we can. As you can see here, there's no common value that can be factored out of all values to get a smooth integer. So we're just going to go on to the next step, in which we would actually look for any value of 12, any two add-ins of 12, any two numbers that add up to 12 that also multiply to 6. So if you look at the values that add to 12, we have 6 and 6, 8 and 4. We also have 9 and 3, all of these different values that multiply out, that add together. But we're trying to look for the two values that add together that also multiply to 36. And if you can see, 6 plus 6 equals 12, and that also multiplies as 36, because 6 times 6 also equals 36. So our values are going to be 6. So we know that in our binomial, we're automatically going to have an x value here, because we know that x is multiplied by each other to get x squared. So that's already a given. Now we need to know what our next value is, and that's going to be 6 as shown here. So it's going to be x plus 6 and x plus 6. That's how you put it out. And as you can see here, we can also utilize the b over 2 squared to see if you have a perfect square binomial with the same given value. So if you have x squared plus 12x plus 36, we can see whether or not this is perfect square by seeing if this qualification is true. So we have b over 2 squared. All you're doing is dividing your b over 2, and that's going to be your given b value, or your given value in your equation, and it's going to basically be b over 2 is going to be 6, which is basically 12 over 2. And 6 squared, does that equal c? Yes, that does equal c. So that means it's a perfect square binomial, in which you can just write it as x plus 6 squared, which is basically the simplified version of this whole equation. All right, everyone. I hope you guys enjoyed today's video. I had a blast making it. This has been the eCoreAcademy e-learning platform. Please make sure to like and subscribe. Also, visit our website at www.ecoreacademy.org to see what kind of new content and interesting content we have out there. Integrated note sheets, quizzes, and worksheets will also be available there at your discretion. Also, visit our socials at Facebook, Twitter, and Instagram. See what kind of interesting content we have there, and use those mediums to share all of our videos. And feel free to communicate with us through our email at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. So that'll be it for today's video. I hope you guys enjoyed. This has been AJ, and I will see you guys in the next one. Peace.